No one.
There won't be anybody, right?
Okay, hi everybody, welcome. So our colloquium speaker today is David Kubiznak, who's joining us from the Institute of Theoretical Physics in Charles University in the Czech Republic. He's going to be talking about black hole chemistry, thermodynamics with Lambda.
Thank you so much, and thank you for inviting me here. It's a great pleasure to be here, and I really enjoyed the morning seminar. So today, I'm going to tell you about this very weird extension of black hole thermodynamics, which regards black holes which are in ADS space, so very, very detached from reality. But you will see that there are some interesting consequences of what doing so. But before actually I jump into that, let me review some high school physics for you, namely that of van der Waals fluids. And so here's the coat of arms of Johannes van der Waals, and he received the Nobel Prize in 1910 for his works on fluid mechanics, and in particular for his famous equation, van der Waals equation. So this is a very interesting extension of the ideal gas equation. It's described simply by two parameters, so you would otherwise have ideal fluid PV equals to T, but now we have two extra parameters, A and B. So A measures something like attraction between the particles, and B actually excludes the volume of these fluid particles. And interestingly, this the very simple equation, this very simple generalization, has been very, very successful in describing various real fluids. And so in particular, if you start plotting the isotherms in the PV diagram, then of course, above the critical temperature, you just get boring and smooth, nice curves like that. But then there is a critical temperature at which you develop the inflection point over here. And then below that critical temperature, you see some weird oscillations. So now you can look at that critical point. Of course, that's characterized by dP over dV and second derivative equals to 0. And it corresponds to these critical values of the temperature and volume and pressure. And you can actually calculate this critical ratio, which is PCVC over TC. And for van der Waals fluids, it comes to be 3 over A. So now, why is this interesting, and what does this oscillation mean? Of course, this oscillation is unphysical. It means that the fluid wants to change the phase from liquid to gas and so on. And you can easily see that if you actually calculate the corresponding free energy, which is displayed over here. So now we have the free energy, which is something like energy minus Ts. It's on this axis, and then you have the pressure, and you have the temperature. And when we plot that, we see this very interesting shape of the free energy. And you see that this thing here sort of looks like a tail of a swallow. So this is called swallowtail in catastrophic theory. And what it basically means is that, there will be some kind of phase transition because you always want to globally minimize the free energy. And so instead of going like up and here and whatever in this tail, you actually go down directly. But that means you are actually changing the phase. So now we can more easily see that in this when you take the p equal to constant slices of this diagram. So now I'm slicing it like that. And you see that above the critical pressure, again, the free energy as a function of temperature now is nice and smooth. But at critical pressure, you see there is like an inflection point, like a small cusp there. And then below that, you see these swallowtails, the slices of the swallowtail. So now if you're increasing the temperature and you start, let's say over here, so instead of going up and up and up, you want to globally minimize the free energy. And so you're going here and directly there. And because the free energy there is smooth, is continuous, but the derivatives are not, you will have first order phase transition. And precisely correspond to changing the liquid to gas and so on. So now this was like a first prediction of phase transitions, and you can directly see them from this equation. So of course now you can also start plotting like when are these different phases, and so there will be a liquid phase and there will be a gas phase, and they will be separated by this coexistence line, where there is this precisely if you're moving from one to another, you have to undergo this first order phase transition. And how you get that point over here is that for given pressure, let's say I have for given pressure, this is my diagram, and I read where this thing here is over there, and I read my temperature, and I get a point there. And for a different pressure, I have this temperature there, and that gives me another point until I reach my critical point where my phase transition will be second order. And then you cannot distinguish above that temperature, you cannot distinguish the two phases. You just have one phase, mixed phase, and so, but you see that basically going from liquid to gas, you don't need to necessarily go like to cross this curve, but you can also go around. So there's like a smooth transition from liquid to gas as well. But if you go this way, there will be a first order phase transition. Okay. One last thing I want to review about these things is that you have this critical point, which is, I don't know why the our volume is there, but yeah, I don't see it here. So we have the second order phase transition at the critical point, and second order phase transitions are nice. They are universal. They are characterized by critical exponents, and critical exponents describe the behavior of physical quantities close to this critical point. So, for example, for this van der Waals fluid, you would define the following critical exponents: alpha, beta, gamma. It's like one. It's like tells you how the specific heat is changing in the vicinity of the critical point. The other one is like what is the jump between the volume of the gas and liquid particles. Gamma will tell you how this isothermal compressibility is behaving, and delta will tell you about the pressure. Okay, and so for van der Waals fluids, you recover this mean field theory critical exponents 0, 1/2, 1, and 3. And of course, you can sort of divide the systems according to universality classes. So typically, if you have a system which has the same effective description, same symmetries, and so on, they fall in the same universality class, and they will have something like these critical exponents, but you can have a different universality class, and so on. Of course, these are only hypothetical critical exponents. They are derived in the mean field theory, and so the realistic ones for the changing will be slightly different because mean field theory is only exact in greater than 4 dimensions. All right, but anyway, so you will see all these concepts now for black holes. So by the way, please interrupt me anytime you have questions, okay? So please ask questions. So here's the plan of the talk. So I'll first remind that black holes actually are thermodynamic objects. Then I will explain to you what I mean by black hole chemistry, which of course is just a term, and we shouldn't be really doing chemistry and mixing black holes and stuff like that. But you will see why we call it that way. Then I will review lots of these very interesting thermodynamic phase transitions of ADS black holes. And then if I have time, which probably I will not, I will tell you about how this can be encoded in the ADS CFT correspondence. And these are the 3 papers which are like the main sources for this talk, but I will refer to some other papers on the way as well. So black holes as thermodynamic objects, and let me start with this, my favorite quote by Arthur Eddington. Well, if someone points out to you that your pet theory of the universe is in disagreement with Maxwell equations, then so much the worse for Maxwell equations. If it is found to be contradicted by observation, well, these experimentalists do bungle things sometimes. But if your theory is found to be against the second law of thermodynamics, I can give you no hope, and there is nothing for it but to collapse in deepest humiliation. Okay. So let's look at the Schwarzschild black hole. This is the simplest black hole you can write down. Everybody knows it. Everybody loves it. It's just spherically symmetric element characterized by single metric function and characterized by this mass parameter m over here. Now you may be asking, what are the characteristic properties of this black hole? And of course, one of them is the asymptotic mass. It's like the total energy into space-time. You can calculate it, for example, using the Common integration. It corresponds to this killing vector, time-like killing vector in your space-time. Of course, time-like symmetry associated with energy. Nobody is surprised that what comes out here is precisely this mass parameter. That's your mass of the space-time. We also have a black hole horizon that's located precisely where this metric function f becomes 0 at that radius, and it's located r equal to 2f. That's this black thing over here. All right. So then we have another, which is surface gravity. That's a little bit less intuitive what it is. Here's a formal definition. Basically, what happens is that your time-like killing vector becomes null on the horizon, but it also becomes geodesic. And if you look at this left-hand side of this equation, this is like a geodesic equation, right? Except now my geodesic is not affine parametrized. You have non-trivial right-hand side, so you have something this is proportional to Ka, right? So that means it's still geodesic, but it's not written in a fine parametrization. And precisely, the proportionality constant here is what you mean by surface gravity. All right, so that's a formal definition. Now, what comes out is this. If you do the calculation, you can show that for any metric which is of this form, you can just get it by taking f prime, evaluate df over dr, evaluate it as the horizon radius divided by 2, and that's what it gives you. In particular, what comes out is m over r plus square. All right, that's a magic formula. Of course, that reminds you the Newtonian gravitational acceleration. If you have Newtonian gravitational acceleration, that's gm, I'm setting g equal to 1 over r squared. So basically, I'm taking the Newtonian gravitational acceleration and evaluating it on the horizon of the black hole, right? Because that's just a coincidence. But basically, you should be thinking about the surface gravity, something like a Newtonian gravitational acceleration on the horizon of the black hole. So now this is a little bit misleading, because if you did calculate something like that, you would find it's infinite on the horizon. So it takes an infinite force to hold a particle on the horizon. So what this really is that force, but now redshifted to infinity. So as you actually try to, if you try to hold a particle on the horizon from infinity, for example, using a massless string or something like that, then this is the force which you would have to have at infinity. So as you climb up the gravitational potential, you redshift, and that's what that kappa actually is. It's like Newtonian acceleration, but now viewed from infinity. All right, so we have that. Finally, we can calculate and decide to calculate the area of the horizon. Okay, we look at the induced metric. We know that horizon is at r equal to r plus, that's 0. We calculated at t equal to 0 or whatever. So these two are gone, and we just have normal spherical element. We integrate that, and we find it's 4 pi r plus squared. Okay, so these are the basic quantities. Here they are again. Okay, we have the horizon, the mass, surface gravity, and horizon area. That comes a great idea. Let's differentiate, right? Whenever you don't know what to do, you just differentiate things. And so you calculate the m, you calculate the a, and you observe a beautiful equality. dm equals 2 kappa over 2 pi dA over 4. That's the first law of black hole mechanics. So we just derived the first law of black hole mechanics, just playing with these basic quantities. But now if you look at that first law of black hole mechanics, what stands here on the left-hand side is something like differential of energy, right? So that's, I told you that mass is like a total energy in the space-time, right? So this, in principle, should be something, could be something that is familiar to you, namely, it could be something like a first law of thermodynamics, right? So on the left-hand side, I certainly have something like the energy. So if I can say that the entropy is related to the area of the horizon, and if I can say that the temperature is related to the surface gravity, then the first law of black hole mechanics is nothing else than the first law of thermodynamics, right? And so actually, this was sort of shown by Hawking in 1974 by using, the QFT space calculation. He indeed shown that if you take quantum effects into account, of course, like classical black holes are completely black. They only absorb things. They don't emit anything. They don't have temperature or whatever. But if you take quantum effects into account, then actually the black holes will radiate away particles as black body at this temperature given precisely by surface gravity over 2 pi. So he really found this Planck spectrum or whatever, and then he could identify the temperature. So now if I know that, then it's obvious that the entropy is given by the area over 4, just from this first law, right? And so by the way, Bekenstein already knew that the entropy is proportional to the area. He just didn't know this 1 over 4. And that came from this Hawking calculation. But since then, people sort of believe that this is true. And there are many other approaches which sort of recover the same result. And so, with this identification, the classical laws of black hole mechanics, which are nothing else basically than the Einstein equations, just written in a different way, become the laws of black hole thermodynamics. Okay. So now, more generally, you can start adding some work terms. So if your black hole has a spin, this angular momentum, this is the corresponding angular velocity of the horizon, then I will have terms like omega dj. If it has a charge, I will have electrostatic potential times T of Q and so on. So by the way, here I'm in D number of space-time dimensions. So that's what this D here stands for, 4 in 4 dimensions. All right, so we can have these work terms, omega dj phi dq. You can have more rotations if you're on higher dimensions. You can have more charges if you have more complicated theories and so on. At the same time, the first law is accompanied by this SMAR relation, which is like a one equation relating finite amounts of these charges. It relates directly the mass to other thermodynamic quantities like that. Okay, these two things are related by dimensional scaling argument, as I will show you in a minute. But then the question is, this looks beautiful, but it doesn't look quite to normal ordinary thermodynamics because you are missing the PDV term. Okay, question is, can you introduce a PDV term into this like standard work term, the most standard work term you can ever have in ordinary thermodynamics? Can you introduce it into this law? And this is precisely done by this picture. Okay, we will introduce a negative cosmological constant. Negative cosmological constant actually acts like positive pressure, and so it will actually push on our black hole, and it will precisely provide this PDV. Okay, so that's the idea of my talk. So here, this is precisely what I just told you. Well, let's consider, instead of asymptotically flat black holes, let's consider ADS black holes. So it's basically black hole, just put in ADS space-time, so asymptotically we get ADS asymptotics. So now let's identify the cosmological constant with a thermodynamic pressure according to this formula. This is something that cosmologists have been doing forever. Okay, it basically is saying, well, I can treat cosmological constant, I can put it on the left-hand side of the Einstein equations and treat it as a part of geometry. And then on the right-hand side, I have T mu nu, or I can move lambda from left-hand side to the right-hand side and treat it as a T mu nu. And the cosmological constant has exactly the form of perfect fluid, energy momentum tensor. And if you were asking what is the pressure of that perfect fluid, precisely that. Okay, so it's just identification of lambda.
I'm a little confused. How come the metric does not appear explicitly anywhere? You're just saying I'm just going to add a PDV term.
You will see. I haven't introduced it yet. Okay. So you will see. So at this point, I'm just introducing. I'm assigning positive pressure to negative cosmological constant. Okay. So these two, I think nobody can object. So now let's make lambda a dynamical quantity. Okay. So now this you may object. Right? How do you? Well, lambda is a constant. It's a coupling constant I add to my Lagrangian. Question is, can you make it dynamical? Well, we know that lambda is dynamical in the real world, right? Definitely different lambda at the beginning of the universe than it is now. And so there are many ways how you can make it dynamical using some more fundamental theory. So for example, there's this Teitelbaum and Brown prescription from the 80s where you say, well, actually, lambda is related to a 4 form in the space-time. It's like a Maxwell field, but now 4 form. And it can, well, that 4 form sort of behaves like lambda, but it can change value. Okay, so that's one way. So for example, in 80s. There's another way, like you can treat lambda effectively as, some scale, well, you can have some scalar field, fundamental scalar field in your theory, and you can be asking, like, what is the effective lambda emerging from the scalar field? And you can start dynamically changing that. So for example, what people studied here, that they studied like what happens with black holes as you have the slow roll inflation, the beginning of the universe, and you're effectively changing lambda. Finally, there's this amazing model which comes from like brain world scenarios and whatever. So what these people here shown is that if you have like a brain in the ADS space or whatever, then you can adjust its tension. And basically, adjusting its tension means moving the brain away from the center or more towards boundary. And so in principle, this motion of the brain adjusts the tension of the brain. But now the variation of this tension is precisely related to the variation of the cosmological constant on the brain. Okay, so basically, like there is a way how to make this lambda dynamical, and I can tell you more if you are interested in the end. Okay. So at this point, let me just assume that yes, lambda is not a constant, but maybe there are ways how to effectively vary it. Okay, so let's just treat it as a thermodynamic pressure. Questions? No? Is there no question? Let me continue. So now, if I do that, then it was shown by these people over here that your first law, that was your question, now gets extended. So before we just had TdS term, but now we have something delta P term. And this was they derive it using Hamiltonian methods that indeed this is the case. But what is this theta? Well, just from dimensional argument, right? This has to have units of volume. So we are recovering a VdP term, right? It just has to be like that. So very good. So we can claim the victory, and we have the standard work term minus PdV. Well, wait a second. I'm writing BDP and not minus PdV. Okay. So not quite. What does that mean here? Is that we have to do a Legendre transformation from normal situation. In other words, M, the mass of the black hole spacetime in ADS, is no longer an internal energy as you know it from thermodynamics. It's a different kind of energy. It's an energy related. So this is my internal energy, and that's my M. So now you open a thermodynamic textbook, and you'll see that this is an enthalpy. Okay, it's a different kind of energy. So now, once you start varying cosmological constant, M has a different interpretation. It's an enthalpy. What is enthalpy? Enthalpy is an energy to create a system and put it in the environment. Chemical enthalpy. Okay, so now that's precisely what we are doing. We are creating a black hole, and we are putting it in the environment of cosmological constant. Right. So it sort of makes sense that mass no longer is an energy, but rather the bulk is an enthalpy. Another thing is, well, if I look at this formula here, I sort of have that I can define the volume of the black hole spacetime as dm over dt. Right? Let's take that as a definition. Let's calculate it for Schwarzschild black hole. We know what m is and we know what p is. You find this amusing formula. It's like 4/3 by r plus q, where r plus is the horizon radius. So now we have like the Schwarzschild black hole is like a ball in the Euclidean space of the radius r plus and so on. And that gives you the one. Yes.
So you're getting all of these magical formulae always with r plus. Is that true when you spin the black hole? Is it still r plus?
That's a very good question. So the answer is well, okay. So this volume here will be much more complicated. So then if you have rotating care or whatever, you have angular momentum as well. You have the A parameter and so on. So this volume formula will be now much more complicated. That's a very good point. So now the question is, okay, now I have more complicated formula. How do I know this is still a good definition of volume? And the answer is there is something which is called isoperimetric inequalities. Okay, if you have a good definition of volume, you satisfy these isoperimetric inequalities. So this was first studied here. I mean, and then very recently there is some new twist on this. So when you have this, Kerr volume, right? Is it still a good definition of volume? Is it still nice a formula? And here is the isoperimetric inequality. It looks horrible, but basically what it means, I have a region, and that region has some area and has some volume. Okay, so now you take the volume to some power so that this is like has units of length, and then you take the area to some power so that it has units of length. Now I divide the two numbers and I get a dimensionless quantity r. Okay, that's what's written over here. You're also dividing it by the volume of the sphere, but that's like 4 pi or whatever, right? So you take that, and then if you are in Euclidean space and you have normal regions in that Euclidean space, this isoperimetric ratio is always smaller than equal than 1. Okay, that's in Euclidean space. Now Gary said, well, it's obvious that for ADS black holes it must be exactly the opposite. I still don't know why, but what you get is this very interesting thing. So we have just seen that this is the volume of Schwarzschild ADS black hole, right? The area is pi r plus square. So it's basically like dividing r plus to r divided by r plus. It gives you r equal to 1 for Schwarzschild ADS, right? Now if you take any other black hole and you fix its volume, that thing will have smaller entropy than, so now we have the area is related to the entropy, right? So this bound is saturated for Schwarzschild-ADS black hole, and it tells you for given volume V here, the entropy is maximized for Schwarzschild-ADS. For Kerr, it will have small entropy. So it sort of tells you that Schwarzschild maybe is a final most stable configuration with the maximum entropy. It gives you some kind of inequality, something like Penrose inequality. But now what you are doing is you are fixing a strange quantity, you are fixing this thermodynamic volume, and then it tells you, well, Schwarzschild will have the minimum, will have the maximal entropy, and then everything else will have a small entropy than that. So that's a good thing. So that's certainly satisfied for we check that for a wide variety of black holes, and makes sense. All right. One last practical reason why you should vary lambda is this consistency between the Smart relation and the first law. Right. So let me start with this Euler theorem, which is just a mathematical formula. Well, let's have a homogeneous function which obeys this property here. Then the following equality is true. So now, for a black hole, the mass of the black hole is a function of the area and the pressure. And now, basically, what everything here, this homogeneity and stuff like that, you can show it explicitly that it's true. But basically, it boils down to a dimensional argument. So you know that the pressure goes like lambda, and that goes like 1 over length squared. The area goes like r plus squared, so it goes like L squared. And the mass goes like r plus, so it goes like length power 1. Okay? So these numbers are important. They are precisely those numbers P, Q, and R, which will appear over here. So then you see I have mass is L to 1, so it's 1 times m, and then A is L to power 2, so it's 2 times A, the m over the A. And then finally, pressure is -2. That's why there's a -2 over here, P times dA now. So now, if you vary the thermodynamic pressure, if you vary lambda in the first law, it tells you what this dm over the lambda is. It's something like volume, and dm over dA is something like kappa. And you find the following Smart relation over here. See explicitly V and P are present in that Smart relation. Yes.
Is lambda explicitly only a function of time or
So
space?
In principle, it can be both, right? But you have, what I'm describing here is like a thermodynamic process. So it has to be like slowly time varying and whatever, right? So and so that's equal to them like equilibrium and so on. So yeah. Okay, so this VP term is here. And if you didn't vary, lambda in the first law, you wouldn't know that it should be there, because you wouldn't know what that thing is. Simply, we wouldn't have homogeneous function. And of course, the Smart relation wouldn't work. So this was actually a puzzle at the beginning, like people didn't know how to write down the Smart relation for ADS black holes, because they didn't know how that this term should be here. Then simply the asymptotically flat one is not true, right? You need the term there. All right, so here is the summary. So instead of that, for asymptotically flat black holes, if you are now in D dimensions, I think what you should be having is that you should be varying this lambda here, and then your Smart relation gets modified like that. But there are many other advantages of considering ADS black holes, and so one of them is actually if you have asymptotically flat black holes, they are really not well defined. The thermodynamic enthalpy is not well defined. You have negative specific heat and stuff like that. Here, you actually have well-defined thermodynamic enthalpy for ADS black holes. And as I will try to show you, they exhibit various interesting phase transitions. And finally, if you believe in ADS-CFT correspondence, everything what happens in the bulk should correspond to what happens on the CFT side, and then they should have some interesting implications for quantum field theories. So, questions? Example. Yes.
I keep waiting to hear about symmetries. So when I think about phase transitions, I think of symmetries, at least in the thermodynamic sense. Are you going to discuss those?
No, I'm not. But I would like to have a discussion about that. That's a good question. Yeah. So here I'm basically doing phenomenological thermodynamics. right? I have a thermodynamic system. I look at this free energy, and I see what possible phase transitions I can have, right? Where that comes from, what kind of underlying symmetries are there? We can explore.
I mean, because you talk about gas and liquid and
Yeah.
ice, and this all comes from symmetry. So.
Yes, true. Yeah. So let me give you an example of what I'm doing. Just maybe I'm doing like very nice things here, right? So let's consider charged ADS black hole, right? So you have Schwarzschild. Now you put Q squared over R squared. I'm putting Bryson and Nordstrom, and I'm putting ADS asymptotics. That's R squared over L squared. It's charged thing, so I have Q over R as my vector potential. Now I can calculate all my thermodynamic quantities in the same way as I was doing for Schwarzschild before. So mass is just this mass parameter over there. Entropy is just area over 4. Volume actually turns out to be again 4/3 pi r cubed. Temperature is just F prime over 4 pi as we had before. That's my formula for the temperature. And electrostatic potential is just Q over R plus. All right. So now you can also write down what is free energy, M minus Ts, and we will be plotting that free energy, what's actually doing. But now if you look at this formula over here, that's the temperature formula, you write it as a function of R plus and L. But I told you, well, let's associate L with pressure. So L is pressure, and R plus is volume. So what this equation really is, it's like temperature is a function of pressure and volume. It's your equation of state. Let's see how that looks like. All right, so again, this is what we had at the beginning. That's the one that was fluid. And here is that equation, which counts for the Bryson and Nordstrom ADS case. That's the temperature equation. You see, it's not exactly the same, but actually it has qualitatively the same behavior as the one that was thing. In fact, amusingly, if you find again, they have a critical point and whatever. And if you form the critical ratio, it comes to be exactly 3 over 8. It's exactly the same critical ratio. Amusingly, I don't know why. All right. So now what's happening here is that instead of liquid and gas, as we had in this picture here, we would have like a small black hole and large black hole, and there will be like a phase transition from the small black hole to large black hole. It's maybe better seen in this free energy diagram. So we have seen that already. So again, now I plot the free energy, and you see, I see these nice flow tails for pressure smaller than critical pressure. And then I will have an inflection point that's my critical point and so on. And, it's very, very analogous to the standard one that was fluid. And you can plot the corresponding coexistence line and phase diagrams and stuff like that. And indeed, you will have like a small black hole here and large black hole. So sorry, why maybe I should have explained this. So when you are plotting this thing here, you are plotting that parametrically. So free energy is a function of P and R plus and Q. I am fixing Q. I'm in canonical ensemble, so Q is fixed. I am fixing always P, and so all things which I vary is R plus. So similarly, I have temperature as a function of R plus. So this is like a parametric plot as R plus is increasing. So you have small black holes here, and then you would go like that, and go like that, and you would have large black holes over here. But of course, then there will be a first order phase transition at this point from small black hole to a large one. Okay, and that's precisely described by this phase diagram and so on. And now, if you look at this critical point here, surprise, surprise, well, it's a simple equation. So it's maybe not that surprising. You'll find exactly this characterized by field theory critical exponent. All right.
So
yes,
I'm having little difficulty visualizing this left-hand diagram. So normally when I have a phase transition, I think of an experiment, right? Maybe I just push it, change the volume or something, and the guy makes a transition from one state to another and all that. What is the experiment I should have in my mind?
Very good. So let me refer to an authority here. Let me refer to maybe more known Hawking phase transition. So what happens over there is that maybe the I want to be.
So is it only your mass that's changing in this? So It seems very counter to the idea of a phase transition, if all you're doing is changing the mass of the
But this is a
black hole.
charged black hole, right?
This is a charged black hole, so
Yeah,
I'm
so-
keeping the charge fixed.
Like, he's
This
keeping the charge
this
fixed.
wouldn't work with with a non-charged black hole.
So, very good. Let me show you, because you started asking, do I have the picture? Here. Just a second. It's important to have questions and address them. There we go. Here's the Hawking phase transition, okay? So what happens? So I switch off the charge. I now have charge Q equal to 0. And so the free energy looks like this. It's very simple like that. It just goes like that. There's small black holes here. Then, you know, you keep increasing the radius. Then there's a cusp here. And then you have large black holes there. Small and large means like, are they smaller than cosmological radius or bigger than cosmological radius, basically, right? So this is something like R plus equal to L. And then you have large black holes, right? So that's fine. Now you can show that this branch is actually not interesting. Small black holes have negative specific heat, it's thermodynamically unstable. This branch is thermodynamically preferred, it has positive specific heat and so on. So large black holes are better, right? But that's not the whole story. The whole story is that, well, there can also be like a radiation present in your ADS spacetime, right? And in that case, you can show that the free energy of the radiation, you can take it to be 0. While Hawking and Page, they really did, like they started putting radiation quanta in the ADS space, and they calculated what's the free energy, and it sort of goes like negative. But then, you know, when you compare it to the free energy of the black hole, it's basically 0. So anyway, so I have radiation going over here, and then I have black holes like that. Now you want to globally minimize the free energy. So you see that in this range of temperatures is the radiation, which is the minimum. And then in that range of temperatures, for temperatures greater than that, is the large black hole there, right? So now I have a first order phase transition from radiation to large black hole phase, right? So that's what you know is you know, like people believe in, and so you can think about it like I have radiation in my ADS. Well, ADS is filled with radiation, and now I start increasing the temperature. How do I do that? Well, complicated. What Hawking and Page argue, well, I can couple this to I can couple the whole universe to a path of external thing, and that will start pumping energy into my universe. So of course, it's a hypothetical, right? But
It's not just the mass that is transiting, it's.
So you have to you have first order phase transition, right? I have to provide latent heat and stuff like that. So I have to really pump energy into the system. And they say, well, let's do it, right? I have the whole ADS space time, but now I have external universe, like external mass, and that will start pumping energy into my system. But then, you know, your radiation is happy for some temperatures, and then at some point, you know, it doesn't like to be a radiation anymore. It sort of collapses to form a black hole. This is a thermodynamic phase transition. It's not a classical one. But, you know, that's what typically people say when they have Hawking phase transition.
It can collapse either to a big or a small, depending on whether it goes up or down that line.
Right, but thermodynamically preferred one is the one which has the lower energy. So this will be the thermodynamically preferred one. So similarly,
But then that large black hole is not really related to that small black hole. In the conventional way, which we.
they are disconnected branches. I definitely agree.
Okay.
Right, and so similarly here, you know that, you know, if I am a liquid and I start evaporating it here, well, I can go directly here to form this, you know, a gas, but in principle, I can sort of overheat the liquid a little bit. So I will a little bit be here on this upper branch, right? But then I fall down directly, right? So that's also possible in nature that you sort of, I don't know, you have you are freezing the liquid, and then you know it's already below 1 degree or below 0 degrees and so on. But then you kick the system and it suddenly crystallizes and form ice and stuff like that. So in principle, you could be for some time in these unstable phases, but then you know if you kick the system, it actually will fall down to the system which is the minimum of the free energy. So here but standardly would have first order phase transition between small black hole and large black hole, and you know the same critical exponent. So now we can, okay, so I showed you already what happens in the simplest functional ADS case and what happens with charge. But you can start playing with other black holes, right? You can add rotation, you can add more charges and so on. And interestingly, what you find is that you find very nice similarities with everyday thermodynamics. In particular, you can find something like solid liquid gas phase transitions. Well, not quite. So in solid liquid, so typically this coexistence line goes forever. you have to melt a crystal to actually, you know, the fundamental difference between crystal and liquid. Here you find another critical point, right? But anyway, so it's like small, intermediate, large black hole phase transition, and so on. You can also have, you know, other things like reentrant. I will show you what reentrant phase transition is. I still have some time. So
going back to the previous question,
yes,
in all of this discussion, this T is mass of the black hole, but also a radiation path. Is that how I should visualize it?
So very good. So in the Hawking page, we had the radiation part.
Yeah.
And then we had the black hole part.
Right. And
So
they are supposed to be in equilibrium, right? It's an equilibrium system.
So yes, exactly. So now in the canonical example, where canonical ensemble where I fix the charge of the black hole, there is nothing like a charge radiation.
Yeah.
Okay. So there you cannot have like just a phase where you would have charge radiation. And so there you are really transiting from a black hole with radiation to black hole with radiation, small black hole to large black hole. Does it answer yours?
Right. So here again.
Yeah. So here again,
we are talking about the radiation exists, the black hole is there, and of course it's in equilibrium, so it's the same temperature. That's equilibrium, thermodynamic equilibrium.
Exactly.
Okay, good.
Yes, yeah, exactly.
Got it. Yeah.
More questions? So let me give you this example of this reentrant phase transition. I don't know what that is actually. And so here's a definition. I think it's really interesting. So a system undergoes a reentrant phase transition if a monotonic variation of any thermodynamic quantity results in two or more phase transitions such that the final state is macroscopically similar to the initial state. Okay, so I do something with the system. I start with the system in one state. I do something, you know, I have this phase, that phase, that phase, that phase, but then I end up with the same phase as I started. This is the coolest example we could come up with. It's actually the first described one. And so what you can do is it's an experiment you can do at home. So if nothing, you know, attracts, if you find my seminar completely out of reality, this you can do at home, right? Do it at home if you smoke. So you can try to find a mixture of the nicotine and water, right? So what is in this diagram is the percentage of nicotine from 0 to 100%, and what is on this axis is the temperature of the mixture. So now you see this weird bubble here. Okay, there's a bubble. If you are outside of the bubble, then you are in homogeneous mixed state. So it's actually, you know, the nicotine dissolves in water, and you have like a homogeneous phase where nothing can be distinguished, right? So that's outside of the bubble. But then if you cross inside the bubble and suddenly you form two layers, you form a layer of nicotine and that separates from water. So you have like layer of nicotine and layer of water. In fact, there is like another interesting jump. Like if you cross this thing here, where one layer is up and the other one is down, and if you cross that bubble over here, they swap. Okay.
Is it
So-
nicotine liquid or nicotine gas? Nicotine gas? What is it?
This is water and nicotine.
Okay.
It's water and nicotine. Yes. Exactly. So if I start here, I start with a homogeneous phase, then I separate two phases, then the two phases swap. But if I keep increasing the temperature of the system, then you mix them again. Okay, try to do it at home. So we start here with a homogeneous phase, and then we have a homogeneous phase again, right? So that's like a reentrant phase transition. And to make the long story short, it's like there's always like this happens when there are like a couple of competing effects, right? And then it's like we always get one phase when, you know, one competing effect wins, and then you get another phase when another competing effect wins, and so on. And so, you know, what happens is we have multi-component mixtures and stuff like that, right?
Can you buy liquid nicotine?
Yeah, I think I haven't tried. Maybe I should try.
You're telling us to do it at home.
Exactly. Well, I keep telling this to my students, right? So, I have good excuse. I don't smoke, so
Vape, but like extract the nicotine.
We have
You won't ask Helen. how to do it.
So anyway, so you can basically see something like that happening for black holes. If you are sufficiently complicated, you can go from large black hole to small black hole, but jump back again to large black hole, right? Another interesting thing is, well,
So in these examples,
yes.
what you call the small black hole, it is stable or is it still an unstable solution?
So you have to always check, right? Is this
Yeah.
a stable situation?
Yeah.
Am I transiting from, we have never seen an example where the minimum of the free energy would correspond to unstable black hole. They are always thermodynamically
Okay.
stable. So if you are transiting between minima, then you are sort of, well, I don't know if you are guaranteed, but we are always seeing that you are transiting from stable to stable. So
Okay,
that's fine.
okay,
It's typically though the small, those which don't correspond to minimum, they have negative specific heats and whatever. Right. So yeah, be stable. Just to amuse you, one more thing is that, well, we went to some crazy theory, low level gravity, doesn't matter what that means. We went to hyperbolic case of the horizon topology. We went to 7 dimension, I think, and so just crazy black hole, whatever. But what we've seen is very interesting. You see that in that case, you have one swallowtail here, and you have another swallowtail, like a reverse swallowtail over there, right? That's for some fixed parameters. But now if you start tuning the system, you can actually move these closer and closer together. And so at some point, the two swallowtails meet at the point, and that's what I think people called before, like an isolated critical point or something like that. And it's an example of a critical point which has different critical exponents than the standard field theory critical exponents. So just to see that you can go beyond like the traditional field theory, but it's a crazy construction, and it corresponds like meeting two swallowtails together. Okay, let me skip that. I have still maybe 1 minute. So just a message, if you care about ADS-CFT, yes, the question is, what is the interpretation of this VDP term on the dual CFT side, right? So in the bulk, it works amazingly. You have these, rich structural phase transitions. They are reminiscent to whatever you know in standard thermodynamics. But where does this fit in the standard ADS-CFT dictionary? And in particular, what you have to be answering is the following 3 puzzles, right? One puzzle. I showed you that in the bulk we have the SMAR relation, which is this equality between the energy and other quantities and stuff like that. And it has these D-dependent factors. Okay, so it's like D here and there's D here. So it depends on the number of space-time dimensions, it's different relation. However, on the CFT, when people formulate it like they are interested in something which is called Euler relation. That looks like this, but doesn't have D-dependent factors. Okay, Euler relation doesn't have dimension dependence, it's just the same in any dimension. So how these two are related, right? Can you really prescribe whatever is happening, in the bulk to whatever is happening on the boundary, even with this PV term, so that these two somehow are okay in any dimension? Another question. I showed you, I was arguing that if we have variable lambda, then you should be thinking about the mass of the ADS black hole as an enthalpy, different kind of energy. But what's actually been known on the CFT side is that something related to mass translates to the energy of the CFT, and that's an energy. So M should be energy on the CFT side, but I was arguing it's an enthalpy on the ADS side. And it's another question. And finally, we had this PV in the bulk, pressure volume term in the bulk. But of course, that doesn't translate to PV of the CFT. Well, in fact, the CFT volume is not very physical because you have conformal field theory, you can blow it up, you can scale it, whatever. So this shouldn't really, like the volume of the CFT should not matter too much, right? But we have seen that, the volume and the pressure here on the bulk side, it really matters. The volume is the control parameter. It tells you how big the black hole is. It tells me I'm in this phase or in that phase, and I have a phase transition between the two, right? But here, the volume of the CFT should not matter. And then, we can go and grind through the story. And now this is the first proposal people are doing. Maybe this VDP term corresponds to something like the variation of the central charge in the theory. But it's slightly more complicated than that. Well, the central charge depends on the ADS radius and the gravitational constant. But you also have the CFT volume, and that typically also depends on the ADS radius. And so you would have like two terms which are dependent. Mu dc term would be dependent, and G Newton. So anyway, however, you can do it, and here's the answer. Yes, you can have the corresponding holographic thermodynamic law, which looks like this. You will have mu dc term, but you have also the variation of the CFT volume term. And this is precisely how you rewrite the bulk first law. So you take the bulk first law, and you take the smart relation there, and you write it in terms of the boundary first law and the standard Euler relation, as you know it from normal thermodynamics, and the equation of state for the CFT. So I don't want to go over time, so let me summarize. So thermodynamics is a governing principle, and black holes are not an exception. And so we've seen Eddington's quote, so I think the thermodynamics is the governing principle for everything. So now black hole chemistry, or thermodynamics with variable lambda, I think it provides an interesting framework for this idea of black hole, how to extend it, and to make it look more human, I'd say. So once you have this pressure volume term, then really all the phase transitions of these black holes, which would be there anyway, just look like the standard phase transitions in ordinary thermodynamics. But you have extended first law, and now this will be consistent with the extended smart law. The smart law will not be true if you don't have PV term. It changes the paradigm on what the black hole mass is. It has to be enthalpy rather than internal energy. It provides you a way of defining something like a black hole volume. And it comes out to be this 4/3 pi r cubed for Schwarzschild, but more complicated for Kerr. And you can uncover these various phase transitions, which are very, very similar to thermodynamic systems. And I show you this one about criticality of charge black holes as a kind of an example of that. But we stop here, and if there are more questions, I'll get to answer.
There's something on the thermodynamic side, the classical thermodynamic side, that corresponds to the, for instance, the energy description in the conformal field theory side of the description.
So this is a very good question. So I don't know. So for example, we have seen here this van der Waals criticality, and we have seen that for certain black hole, for certain charged black hole, you have a second order phase transition, right? You have this critical point there, and typically that means that you have some conformal field theory description somewhere, somehow, right? I have not identified it. So that would be a very interesting thing to do, I think, because yes, we have second order phase transition. There should be a CFT description somewhere, somehow, and that's where it comes from. But yeah, it's a bit.
So yeah, I'm still completely confused about the story in the book. So these large black holes that you're referring to, I have two questions. The large black holes that you're referring to, so what are they? Are they kind of like empty the cyberspace with a cosmological horizon, or what is
it's all about that you have another scale in the problem, right? So if I am asymptotically flat, the only scale I have is the mass or the radius of the black hole, right? But now I'm asymptotically ADS, so I also have another scale in my problem, is the ADS length scale, like how big the cosmological constant is and so on. And you can write L, it has really units of dimensions of length. Okay, so there's a L is the scale of the cosmological constant. And now you can start comparing how big my black hole is with respect to this additional scale I have. So if R plus, the horizon radius is much smaller than L, then I would be saying, roughly speaking, I have a small black hole. And if it's bigger than L, then I will have large black hole. So now it turns out that the behavior of small black holes is very, very different than the behavior of large ones. So if you have a small black hole, I have teeny tiny black hole in an ADS space with large L. So that black hole really doesn't know that it's in ADS space because it's just too small. It doesn't know about the ADS scale and stuff like that. So small black holes in ADS space will behave like Schwarzschild black hole in asymptotic flux case. They will have negative specific heat and stuff like that. So small black holes are sort of Schwarzschild-like and thermodynamically unstable and whatever. But now, if you have the opposite limit, if you have a large black hole, then of course it knows it's an ADS because its radius is bigger than this L, right? So it's a really, really big black hole. It knows that the asymptotics is different. And that one has very different behaviors, positive specific heat, it has negative free energy and stuff like that. So very, very different behavior, right? And so then it's always like the competition between, like if I start increasing the radius, right? At some point I will be more like Schwarzschild-like, and another point I will be more like this ADS black hole-like. And then you can have various phase transitions, stuff like that.
So sorry, so the second question I had was, so as you said, you have your critical point here. You can go like this from big to small black hole, or you can go around here. So there must be a way that you can continuously go from the normal, what I used to see as the normal Schwarzschild black hole, and what you describe as some exotic thing that I still don't understand what they are, a large black hole. So what is this term? If I follow this, what
That's certainly true, right? So you can either cross through the first order. I shouldn't have said that, but okay, it's definitely true. I can either undergo the first order phase transition going like that, or I can go around it like that. And it's because like if you are as you are going around, you are gradually changing the properties of your black hole, and then you will realize I can actually smoothly do it, right? And in the end, I come up in this phase, and that's absolutely fine. Right, so it's like liquid gas, right? I can really, if I start heating it up or whatever, then I don't have to undergo the first order phase transition, but I may end up with the same gas in the end, right? And so yes, you can avoid it like that. I think another interesting question is like, if you are undergoing this first order phase transition, well, I know what it means for liquid and gas. I'm just, I have evaporated part of my liquid. I still have remained some liquid and some, so I'm doing that. But what I'm doing with the black hole, right? Do I have a superposition of small black hole and large black hole? What's happening there? That's certainly an interesting question I don't have answer for. So as we are changing this first order phase transition, it's a thermodynamic phase transition from small to large. But what does it mean really? What do I have some kind of, I don't know.
Yeah, this will be kind of a fuzzy question. All of your analysis was about one black hole sitting in some universe, right? ADS or whatever. You never considered maybe, a gas of black holes or, multiple black holes all in equilibrium. And I guess that's because you are always thinking of thermodynamic equilibrium, and the thermodynamical end state of multiple black holes is one big black hole. Is that the reason? Or can I think of multiple black holes following your laws, sitting in this one universe of given L?
I guess you could do that, but the main point is that you can have just one black hole is enough to have like thermodynamic equilibrium and stuff like that. So what we are really talking about is like thermodynamic of microscopic degrees of freedom, of gravitational microscopic degrees of freedom. So in one black hole is sufficient to have this thermal equilibrium of these degrees of freedom there. So maybe
I'm asking whether it's beyond sufficient. Are you saying for this framework to make sense, it's necessary to only have one black hole?
I'm saying no. You don't need to have one black hole. I think it's sufficient to have one black hole, and it's and what you are really talking about is like the space-time thermodynamics, really, right? If you could identify what these microscopic degrees of freedom are. But I think this is a very interesting question. Like, could I consider like a gas of black holes and play the same game?
I think you cannot, because
I think you can.
The radiation field has got one temperature. And if you've got multiple black holes, they will have different temperatures. They're not in equilibrium.
I don't think we know the solution. Right?
They would have to equilibrate first, right? So we would have to.
All the black holes should have the same temperature.
Yeah. For example, a simple example of what you are saying is maybe you could consider black holes in the space, right? So then you know that you have like the de Sitter horizon is at one temperature, and then you have black hole horizon is in general in different temperature. And again, you don't have equilibrium thermodynamic state there, right? You have some
you have to either evaporate or
another flux coming from there, and
exactly.
they are not
They have to
but the same is with multiple black holes, right? So, but let's assume that maybe in the end everything equilibrates, everything is in the same temperature. I think we could do that. Yes, I think it's a good point.
But then shouldn't you also consider this other states where it's not 6 black holes, but only a single black hole, and therefore the true end state is always the single black hole.
Yeah, so I think these are very good thoughts.
That's-
I haven't thought about it. Okay, thanks.
Okay, we are at noon, so unless there's any very quick questions, you can ask David questions over lunch. Thank
Yes.
you.
I think it's a very interesting question.